Welcome to the MOKE instruction video. The purpose of this video is to show you how to care in a time-resolved fashion. I will walk you through the very elementary basics of the method, then I will make a very rudimentary measurement, and in the end I will show you some exemplary studies that can be performed with our home-built system. As you can see in the left part, the actual setup is reasonably simple. The heart of it lies in a pulsed laser. You can see in the right panel that the pulse length is much shorter than the spin wave dynamics itself, and this is the elementary premise for the time-resolved studies. So back to the setup, the linearly polarized light pulses are first expanded and guided to the microscope objective. Here the light gets focused to an approximately 400 nanometer wide laser spot and it hits the sample. When we excite some spin waves with the microwave antenna, the magnetization in the sample changes rapidly. Yet when we synchronize the laser pulses with the RF source, and when the RF frequency is an integer multiple of the laser repetition rate, we can basically freeze the spin wave pattern in time and thus to even measure the DC signal. Now, the out-of-plane component of the magnetization vector will change the polarization state of the incident light from linear to elliptical through the Kerr effect. So when we use a balanced photodetector, we can nicely see those minute changes in the signal. When the smallest frequency step being equal to the laser repetition rate is just not enough, we can shift the spin wave frequency from the perfect n times laser rep rate frequency and then use the lock-in amplifier to demodulate the signal on the beating frequency of the laser and the excitation. With this trick, we can access all the frequencies we desire. As a first step, we need to carefully load the sample on the sample holder. We coarsely position the sample and then we use the manual positioners to get the sample to the focus and also to locate the structures of interest. When we are satisfied with the position, we can bring the RF probes in and contact the excitation antenna. By lowering the probe, it will get more and more to the focus of the camera. When we land the probe, we can also see a finite resistance being measured on the multimeter. As the last step, we bring the piezo wrench to lie between the antennas and we let in the laser light. So now it's a time to slide in the magnet to the sample position and lock it so it stays where it should be. So the sample can now be excited. The laser is in focus, the magnet is in the position. We are ready to do some measurements. Let's switch to the software and verify we have some spin wave excitation. In the bottom right corner we see that the laser spot is nicely sitting like 50 microns from the antenna. So now when I turn on the RF source and also set some magnetic field, we can immediately see some response in the top right panel with a lock-in amplifier module. When I change the field a bit, the signal also changes, so there is some serious spin wave stuff going on. Since we have verified that everything works out, we can set a very simple automated measurement. We will use the central automation program to set a frequency scan for different magnetic fields. First, we define the scanning arrays of the frequency and the magnetic field. And then we also define the order of the automation looping. Now we can just run the script. There is some onset frequency for each field where the spin waves start to reach our laser spot. When the measurement is finished, we can see a spin wave dispersion shift with the magnetic field. Due to the high automation of the setup, there are quite many studies we can actually do. We can perform a magnetic field dependence of the spin wave resonances, study spin wave damping, dispersion, or even record the spin wave's temporal evolution with a spatial resolution reaching 400 nanometers. So you name it, we can measure it.